Good morning, everyone. Welcome to the technical presentation organized by the IEEE student branch of AUT. The talk will focus on energy management of the self-consumption associated to buildings in order to achieve the best possible economic profitability and the highest self-consumption rate. It is my privilege to introduce our speaker for today, Professor Haritza Camblong. Professor Haritza Camblong is a member of the University of Basque Country, Spain. As a full professor, he is currently with the Systems Engineering and Control Department and SI&E Research Group in Donostia, San Sebastian. He is the coordinator of the Master in Control in Smart Grids and Distribution Generation program. He received the Electrical Engineering degree from NCA Grenoble in 1996 and the PhD degree in Control Engineering from NSAM in 2003. After his graduation in 1996, he worked in Ikelan Research Center for 2 years in mechatronics applications. Later, he worked with MSI Engineering Company for another 2 years. In 2001, he joined Estia Engineering School, where he created Energia Research Group. His current research interests include AI-based energy management systems, production and demand prediction, PV power collective self-consumption, and smart grids. He was included in the Stanford University's list of top 2 scientists in the world in 2021 and 2023. Please help me welcome Professor Haritza. Thank you.
Good morning to everybody. First of all, I would like to thank Ramon for having proposed me to carry out this speech. I would like also especially to thank TechLee for having accepted my query to carry out my research stay here. And in general, I would like to thank all the colleagues of the people from the AUT that has been very friendly and very kind, very helpful when I've been here. Then, regarding the place where I work, I am from the University of the Basque Country. You can see here in this map the Basque Country. One part is not of an official country. One part is in Spain, and the other part in France. In the Spanish side, there are 3 provinces that form the autonomous Basque community, and there is the University of the Basque Country, the public university. And I belong on the Faculty of Engineering of Gipuzkoa and on the Systems and Intelligence plus Energy Group, Research Group. And I carry out then, I started this new topic I will present you now in 2020, then in the frame of EKT project. Regarding the topic environment, you must know that especially in Europe, there is a tendency toward a more decentralized, decarbonized, digitized, and intelligent grid. It is also probably in other regions of the world, but I can ensure that in Europe is like that. Then, as said before, the research study I will present here was developed in the frame of EKT project. There was 2 pilot actions in this project, and one of them was in the technology park of Isarbel in the French side of the Basque Country, near Biarritz. And then in this technology park, 3 buildings were involved in the collective self-consumption. Estia 1, Estia 2, and Estia 4. 3 of them, these 3 buildings are managed or owned by the engineering school of this technology park, whose name is Estia. And then in Estia 1, there are some PV panels to produce energy. In Estia 2, this energy was consumed, and in Estia 4 also. Estia 4 is a business center with a data center inside. And during the project, we didn't know. The PV panels of Estia 1 were not yet installed. Then we used some other panels installed many years ago in this roof to emulate all the panel which will be installed, and then the entity, the juridic entity of the self-construction was not created. It is why you will see later we have studied the case of including the data center or don't include in it. Then, regarding the management of energy in the collective self-consumption, we have to differentiate two different approaches, different but compatible. The first one consists on sharing the PV production in the frame of the collective self-consumption. It is to say that we decide regarding the production how we share it between the different buildings, in this case, involved in the collective self-consumption. The second approach consists on acting on building flexible loads in order to shift the consumption and in order to try to follow the production profile. Regarding the first approach, the objective then here in this project was to develop, implement, and validate a PV sharing algorithm. And we had three research questions: how the three sharing method considered that in the French legislation perform according to the self-consumption rate and the savings, and what is the influence of the day's solar radiation on this sharing, and what is the influence of adding a data center. As explained before, during the project, we didn't know yet if the data center of STR4 would be included or not in the collective self-consumption, and this inclusion, as you will see later, has a very big impact on the results. Then, as said, the French legislation consider three possible sharing methods. But first of all, I would like to explain how we calculate the self-consumption rate. In France, it is calculated a posteriori. It is to say, after measuring the production and the consumption each 30 minutes. And it's the sum each 30 minutes of the self-consumed energy divided by the produced energy. Regarding the three possible sharing methods, then the first one is a static sharing. Here we define the percentage. For instance, in our case, there were three buildings. Then we could define that 33% of the production was used for or dedicated to STR1, other 33% to STR2, and other 30% to STR4. The default dynamic sharing, the second one, is managed by Enedis, the French distribution operator, DSO, a distribution operator, and then here the sharing is carried out proportionally to the consumption in each building. The third one, it's the dynamic customized sharing, and here after each 30 minutes we can decide how to share the production. Then we can this allow to optimize this sharing according to the tariffs paid by each consumption in each building, etc. Then we have tested these three different sharing methods. About the customized dynamic sharing and about the interest of defined rules in order to have the best savings. Regarding the calculation of savings, of course, we take into account the price of the electricity bought from the grid, and also the cost, of the electricity by grid, and also the price offered by the manager of the grid for the excess energy, photovoltaic energy of the collective self-consumption. But there are especially two concepts that have to be taken into account: the toll and the taxes. If the energy that is produced in a building is consumed in another building using the local distribution network, then we have to pay tolls. And if the production, the PV panels are owned by a company and the consumption is carried out by another company, then it has to pay also taxes. Okay, in this case, in STIA 1, we have not to pay toll and tax because the panels are from STIA and owner STIA is STIA, and the production is in the roof of STIA 1. In STIA 2, we have to pay toll but not tax, and in STIA 4, we have to pay toll and taxes. Okay, then some IoT was developed and installed for both approaches and to communicate with different sensors, smart meter, etc. Here you can see also this is related to the second approach, the HVAC system installed in STIA 2, where there are 10 external groups, heat pumps, and 73 indoor units. Then these are the results obtained with the 3 different sharing methods. I will not detail everything. Only you can see that there are 4 scenarios, 4 columns, 4 scenarios. In the left, in the first 2 columns, we don't consider the data center inside the collective self-consumption, while in the right columns, yes, the data center is considered inside the collective self-consumption. And you can see in purple, clear purple, we represent the consumption in STIA 4. Then when the data center is considered, of course, the consumption is much higher. In green is the consumption in STIA 2, and in red, the consumption in STIA 1. The blue curve is the production, the PV energy production. And all is in dark colors is the self-consumed energy. In the first line correspond to the static distribution or sharing, the second one to the dynamic by default sharing, and the third one, the dynamic customized. And we consider two different days with different solar radiation, with low radiation or high radiation. To summarize, we have seen that the best self-consumption rate is obtained with both dynamic sharing, and the best savings are obtained with the customer dynamic sharing method. Then in conclusion, yeah, the most interesting sharing method, according to the French legislation, is the customized dynamic sharing that allows increasing the savings. There is a publication about this work in Alien Journal. Then if you are interested, you can, of course, read more details over that. Regarding the second approach, then in our case, we considered the flexible law we considered was the heating, ventilation, and air conditioning system of STIA 2. We have also worked on EV, electric vehicle charging, in another case in Aduna, in Gipuzkoa, in the Spanish side of the Basque Country. And we are submitted a publication with the participation of TechLee also, but I have no time to explain this work. Then we developed 2 types of EMS. One was a rule-based EMS, and the other one an optimized-based EMS based on the model predictive control technique. And the structure of the EMSs was this one. The inputs were the external temperature, the solar radiation, the indoor temperatures, the PV production, and the building's consumption. And the output was the set point temperature of STIA 2 and the on-off state of the indoor units. Then, regarding the rule-based EMS, the objective was to develop and validate rule-based EMS in Isabel Technology Park, and trying to obtain the best self-consumption rate, and of course also respecting the comfort of the users of the building. The research questions were is the real-based EMS, yes, can this real-based EMS lead the consumption to follow or to track the production? And do we ensure the comfort of the users or the best of the building? And as is the self-consumption rate improved with the rule-based EMS? Then, first of all, we defined the comfort of the users in the building. Then we carried out some tests to characterize the behavior of the HVAC, and then we defined the sample time of the EMS. We defined the rules of the EMS, and we defined an assessment protocol because, of course, we couldn't test the EMS during work days in order to avoid to perturb the users of the building. Then you carry out our test in Sunday. Compared with the work day, we selected some work days with similar temperature, external temperature, and we calculated the average consumption of these work days. Okay, then the comfort was calculated or defined thanks to the Bragger diagram that take into account the external temperature of the precedent day, and then fix or define the comfort of with a 90% acceptability or 80% acceptability. We carry out this kind of test. Here in the left, you have 5 indoor units of a room, and in the right, the corresponding external group. And we make some conclusions from there. For instance, that when a new external group was switched on, and the difference between the set point temperature and the indoor temperature was between 3 and 5 degrees, the variation of the consumed power was more or less 2 kilowatts. We also have other conclusions that allow us to define the rules of the rule-based EMS in 2 steps. First, we didn't take into account the comfort. The objective was to see if the consumption was able to track the production. And in the second rule-based EMS, we considered also the comfort. Then the results regarding the first flow chart are shown here. Then in the test we carried out in Sunday, then we obtained a 92% of self-consumption rate. Here you can see the blue curve is the production, the orange is the consumption, the red one is the self-consumed energy, and the purple one is linked to the heat pumps on what we act. Then with the protocol I've mentioned, we can compare the result we would obtain with the rule-based EMS, and in this case we would obtain a self-consumption rate of 71%. Even here, if the objective was not to ensure the comfort, we ensure 80% acceptability comfort. In the second test, the rule-based EMS, the control were operating in heating mode, and we obtained, then it was in winter, and we obtained a self-consumption rate of 89%. Here you have the temperature in each floor. You can see that in the fourth floor, that is just under the roof, we overpass the 90% of acceptability. It was our target that all temperature were inside the 90%. But of course, as the heat pumps were working in heating mode, we couldn't cool that. And this was because of the effect of sun in the roof. And we can see also that in the first floor, which one part is underground, the temperature were very, very cold sometimes, 17 degrees. but it's the temperature given in the 90% of acceptability by Bragger. It's true that Bragger is not maybe a good model for this case, because this building is rather humid. Then we should update a bit the Bragger diagram to obtain a minimum temperature a bit higher. And comparing with, yes, here I've not the figure related to the Procotal I've mentioned, but in general, in winter, the consumption is much higher than this one. Then, in this case, the self-consumption rate that we would obtain in a workday would be 100%, but with less efficiency, because the consumption would be much higher. And if we compare the results obtained with the rule-based EMS with the same result we would obtain if the rule-based EMS was not operating the same day, the self-consumption rate would be of 37%. Then in conclusion, you obtain a good tracking of the production. We respect the user comfort according to the Bragger diagram. We improve the self-consumption rate in summer, not in winter, because in winter users that can use individually the thermostat of their room, of their office, then consume more energy. But thanks to the rule-based EMS, in winter we have a better efficiency. And now, yeah, we are working on a publication with also the participation of Ramon. Regarding the optimized-based EMS, the objective was to design, develop, implement, and validate this EMS in the Isabel Technology Park. The research question were how to develop the needed tools for that, considering the constraints we had, and what and if this, and we wanted to know if this EMS would be better than the rule-based EMS, and to what extent. Here you have the functional diagram of the optimization-based EMS. Then the recovered needed data are of course cleaned and processed, and are used to train some machine learning models in order to predict the PV production and the building consumption for 24 ahead. It is to set up for the 24 hours of the next day, with sampling time of 1 hour. Then the difference of these two curves give then the gap we should try to fill with the consumption of heat pumps. And then we develop a building thermal model and the HVAC model, in order the optimization model can, using the difference between the PV prediction and consumption and this model, decide in the next day what temperature set point apply to the STR2 building. Okay, then one of the tools we had to develop was the consumption forecast model. The constraint were that this work was done during COVID. The IoT install was new, and during COVID, of course, there was some lockdown. There was no consumption. You can see here in this curve, sometimes the consumption, sorry, in STR2 was nearly zero. And moreover, as said before, each user in this building can adjust the temperature in its room, and then the behavior of the heat pump's consumption is rather chaotic. Then the objective was to obtain the model I mentioned before, and the research question was this one. Yes, what are the most helpful input variables to obtain the best forecasting? What time windows use regarding the input variables, and what would be the best the best model, machine learning model between NARCS, LSTM, and the super vector regression. The methodology was this one. In 2 steps, we choose the input selection, then we adjust the model hyperparameters, sorry. Then we select the best, time windows, and we carry out the prediction with the 3 obtained models. Regarding the input signals, we saw that the best input signals to consider were the external temperature, and this occupation curve we created according to the information we had about the occupation of STI2 building. Of course, this occupation curve in weekends and holiday days is 0. Yeah? Regarding the time window, we saw that the best trade-off was to consider a 3-week time window for the input variables. And these are the results we obtained. Considering the rather chaotic behavior, we were rather happy obtaining these results. The NARCS, yes, with the metrics, the NARCS performs 26% better than the LSTM and 21% better than the super vector regression. And this can be explained. The NARCS is a recurrent neural network, and it's able to catch the dynamics of the system. The LSTM also, but LSTM is normally fitted for to work with big data set. In this case, we were working with small data set because the constraints I explained before. And the super vector regression is not a recurrent method. And yes, we saw also that we obtained better results in summer because the HVAC was less used, and then the consumption signal was less chaotic. We have also publication here for people that would be interested. Then another tool was the PV production forecast. The constraints were similar with small data set because new IoT and PV panels. And the objective was also to predict or forecast the 24 ahead production of the next day. We developed this work, in 2 steps. In the first step, we trained the models with measured data, especially measured solar radiation. And in the second time, we used the solar radiation predicted by some meteo agencies. Then the research question were what are the most helpful input variables, and what is the best model between NARCS, feed-forward neural network, and super vector machine, and an analytical model. The method was similar. We saw that the best input, the best was to consider only the solar radiation as input. And these are the results we obtained. Very good result, but of course, we obtained this result with measured solar radiation and not with, and of course, we couldn't do that to forecast the next day because we don't know what we cannot measure one day before the next day solar radiation. Then here we saw that the super vector regression had as the feed-forward neural network another input. It was a time vector, and then it performed 4.07 better than the feed-forward neural network, 5.12 better than NARCS, and 4.18 better than the analytic model, according to R-square metric. Here, the NARCS was not performing so good. We think because it's a recurrent, and the relation between the solar radiation and the production is nearly algebraic. The dynamic is very, very fast. Then it is maybe the explanation of what we obtain a worse results with NARCS. Here we have also a publication in applied sciences. And then in the second step was to train a model that used as input the predicted solar radiation by different meteo agencies. Then the research question were what meteorology agency data give the best results or lead to the best results? Do machine learning models compensate a bit at least the prediction errors, the solar radiation prediction errors, comparing with the analytic model, and what is the best machine learning model? Then we compared, we used data from Meteo Galicia. Galicia, it's a region of Spain. We have access to free data from Meteo Galicia, and Meteo Galicia used USA model, global forecast systems, and they apply also a digital filter named weather research and forecasting. And we use also data from a European agency. It's a deterministic atmospheric model, and it proposes a single prediction that uses observation and also prior information about the Earth system. It is known as being the highest resolution model. Then here I show you the result in a Taylor diagram. You can see in this diagram, in the X and Y axis, we have the standard deviation. In blue, we have the correlation coefficient, is to say R, and in green cruise represent the RMS error. We consider all this scenario. Then we compared the result with prediction based on persistency and random. And here with the different colors, we have the feed-forward neural network, the SVR, the NACS, and the analytical model. And with each model, we use three kinds of different data. MF means Meteo France, is the biggest meteo agency in France. Then it corresponds to measured data. And then MG is Meteo Galicia, and ECMWF, it's correspond to the data of a European agency. Of course, for the model predictive control, here we can only use the models related to Meteo Galicia and European agency model. The best model or the best results are those that are most near if you trace right line between the observation and the point, and the best results are those that have the smallest distance between both points. And we can see that the best results are obtained with the European agency data and with a feed-forward neural network in winter and again here in summer. These are the obtained results with time series for the different machine learning techniques. And then in conclusion, you can say that the European agency data lead to a bit better, slight better results, that the machine learning models are, yes, able to partially compensate the errors of the prediction of solar radiation from the mentioned agency, and the feed-forward neural networks, which is the simplest neural network, leads to the best performances. Then, to finish with the tools we have developed, I will speak here about the model we obtained for the thermal behavior of STR2 building and the associated HVAC system. Then the objective was to obtain linear models to use them for optimization later. And the research question was, what are the most influent variables? Can linear model accurately represent both behavior, that of the thermal behavior and the HVAC behavior? And does NACS allow representing the non-linear behaviors? And does the linearization of NACS perform better than the linear model obtained directly? Then for that, we had to excite the HVAC. And first of all, we carry out a test in Sundays, also on weekends, because we couldn't perturb the workers. And then we carry the first test with the step response. The step response allows us to know what was the setting time between the set point temperature and the indoor temperature. Thanks to that, we choose the sampling time to carry out a test during all the weekend, and we created a pseudo-random binary signal that we applied to the as set point, to the set point related to the heat pumps, and we carry out this kind of test in 3 weekends. We used the first data set or the first weekend to train or identify our models, and the other 2 data set to validate or test the obtained models. Of course, after the data cleaning and processing, we first obtained the linear model by identification, and then we trained the NACS model. Then we obtained the linearization, some linear equation, thanks to the linearization of NACS, and we compared both all models in the above mentioned 2 test data set. Then we have two equations. The first one is related to the thermal behavior. Here, the output of the model is the indoor temperature, and the inputs are the external temperature and the heat pumps consumption. And in the second equation, the output is the heat pump consumption, and the inputs are the set point temperature, the external temperature, and the hysteresis of the error between the set point temperature and the indoor temperature. These are the results of the first equation. We can see here the metrics we have used is the fitting matrix. You have the corresponding expression here. And yes, we obtain good results for this first equation with the first data set for the test 1, and also with the data of the third weekend. For all cases, the NACS that take into account the nonlinearity, the linear NACS, and the Box-Jenkins model, that is a linear model obtained by identification directly. Regarding the second equation, that was much more challenging because the variation are a bit chaotic. We obtained good results with the first test data set, but in the second data set, the results were a bit worse, and especially for the Box-Jenkins model. Then in conclusion, we show that it was very important to consider the hysteresis of the error between temperature as input, and that the NACS model performs very well in both tests. Then now we are working. Here it's first in conclusions, yes, because I have not spoken about the optimization model here. It's because we have not finished working on that. Then as conclusion, we can overall say that we validated the PV sharing in the real system, and also we developed and validated the rule-based EMS with heating mode, and we validated also all the tools needed for the model predictive control. And regarding future works related to EKT, now in another project, named Consumadim, that means in Basque, intelligent consumption, we are then carrying out the completion of the optimization. We are waiting also to have a good day to validate the rule-based EMS in cooling mode, and we hope to implement it the next month and validate the MPC and model predictive control EMS in the collective self-consumption of eServer. And to finish, again with the future works, we have get a new fund from European Union in the frame of the Interreg POCTEPA program. the name, the following of ICATE is ICATE Plus. And there we will focus on other flexible loads as electric vehicle or industrial flexible loads, and will deepen on the tools we have developed with new concepts or hybrid techniques. Then we will recruit 2 PhD in some months regarding this project. Then if you know some students that could be interested, they can contact me to this email address. Now me here, thank you everybody. And now I'm ready to questions.
Thank you, Professor. It's the time for questions now. Anyone from the audience questions?
I think now we will be able to eat. Then, of course, when eating, you can also ask.
Yeah, okay.
Yes, for people that is online.
Okay, so any questions from the online audience? About that. Looks like don't have any questions. Yeah, so looks like we don't have any questions from the online audience as well. So Russell has a question. Okay, yeah. Do you want the mic?
Thank you so much for your for a lot of information that you just presented. My question, first of all, was about you talk about efficiency of your system, and then wait, I cannot find it. Yeah, efficiency and the type of the load that you have in the house. You talk about HVAC. Is there any relation between the efficiency and the type of the load?
Sorry, I don't understand the efficiency and
the type of the load that is used by the consumers in the house.
The type of the load.
Yeah.
Yeah. Well, yes, I mentioned the efficiency when I was speaking about the rule-based EMS. Yeah.
Yes.
Yes. It's because in winter, when we apply the rule-based EMS, we obtain more or less a self-consumption rate of 90%.
Yeah.
While in similar days with similar temperature, the self-consumption rate is 100%. Then we can say, oh, but the rule-based EMS is not good for. But it's true that thanks to the rule-based EMS, the efficiency is better in the sense that we consume less energy, just what we need, respecting the comfort and trying to self-consume as much as PV energy possible. In this case, the rule-based EMS works as a centralized control of the HVAC, while normally in each office there are some thermostat, and the users of each office can choose the set point in his office, and often they also leave the thermostat
automatic.
Yes, switch on, etc. Then yes, we saw that thanks to the rule-based EMS, we have a better efficiency in winter. Yes, related to the HVAC, yes, consumption, the consumption of the HVAC.
Yeah, thank you. So the next question, you said that the best result you would be able to receive after collecting data and train your model based on 3 weeks of having data, right? And what is the sample rate of collecting data in this case? Sample rate of yeah.
Yes. This was for the prediction of consumption. The sample time asked for the prediction for of the production is 1 hour. 1 hour.
1 hour.
Each, hour.
Like one sample data per hour.
The input data, we have the input data with a sample time of 1 hour. And we use the 3 last weekends information related to the input data.
Yeah.
Then 3 multiplied by 7, multiplied by 24. These are all the data we use for each input data.
Yeah.
To predict the
future consumption.
The 24 hours of the next day.
Yeah. Isn't it better to go for a more finer time step, like 1 minute or 1 second? Because there are already some methods like non-intrusive load monitoring, NILM, that they collect data one sample a second. And
the accuracy with this low sample time will be very much more bad. And it's true that it would be more interesting to use 30 minutes sample time, because in France the self-consumption rate is calculated every 30 minutes. But as a first step here, we used 1 hour sampling time. Anyway, in the literature, most of people use 1 hour sample time.
Yeah.
For this kind of application.
And about the methods, machine learning methods that you used, recently some people came up with some methods like that based on attention, like transformer, like Mamba, which is quite new, and you haven't used them, right? New methods of neural network or deep learning methods, like transformer, which is based on attention.
Every model, we have 3 models.
Yeah, right.
2 models of 2 forecast models.
And one was LSTM.
Yeah, I mean, we have designed and developed 3 models.
Yeah.
One is related to the production forecast, another one to the consumption forecast, and another one is related to the building, theater building thermal behavior and the associated HVAC behavior. Then when we are mentioning these
tools, yes.
They are for what models? Every model?
Oh yeah, every model.
Yeah.
I mean,
yes,
the efficiency or the.
Yes, there are many.
Yeah, we're right.
Techniques, and it's true, as said before, for me and my students, this machine learning and AI tools were new. Then we choose some ones, especially recurrent ones, and we tested them. But yes, of course, there are many.
You're right.
Moreover, there are many more and more hybrid models also.
So that's the part that yet to be investigated in the future. Yeah, thank you so much. Yeah, thank you.
Thank you, Russell. Do we have any more questions?
Yeah.
Thank you very much, Professor, for a very interesting presentation. So many topics, or research topics, have been presented in this moment. The first questions, also allow me to introduce myself. My name is Denny Hamdani. I'm lecturer from Bandung Institute of Technology, Indonesia. I was classmate of Professor Ramon. And also my former students, FE here. So very delighted to visit these guys, and also thank you very much for the insightful presentation. So my first question is the first topics you have shared about the consumption, how to manage the PV production in terms of consumption, right? So is this research results is applicable in the real distributions so company for example in Spain have the distribution company applied these techniques, or because in Indonesia it's not applicable yet. So.
Legislation is very different from one country to another country, which probably some countries there is no legislation.
Okay.
But yes, for instance, in Spain is different. You cannot carry out dynamic share. Then I'm sorry, no. In France, yeah, you can. Moreover, now it would be a new opportunity. If you have different PV panels installation, you could define the sharing method for each production, even if it's in the same collective construction area. But then, yes, no, this sharing depends really on the legislation of each country.
Okay. And what about in Spain? Probably we can learn something from them.
In Spain, it's changing, but at the beginning, you could only apply static sharing, defined before the sharing, and now you can define variable sharing, but define also before. Always the same sharing. You calculate, for instance, statistically what would be the best, and you define it for the next 8 months, something like that. And it can vary. I mean, for instance, according to seasons, it's not static, but it's not enough. And the self-consumption is calculated every hour, while in France it's calculated every 30 minutes.
So, and the second question is that as you applied so many optimization techniques to optimize the system and energy management from PV, right? So, and of course, the results depends on not only from the characteristic of the optimization technique itself, but also the quality of the prediction data, right? So, and you have shared, show us that the European agency also give a better data also to so for your model. So how so the question is how significant actually also the quality of data also in terms of your research here.
Yeah. Yes. In order to try to get the best results, to have different possibilities, you can try to use the best technique and train them as possible and tune the hyperparameters corresponding to methods, etc. And you can also try, and I think it's the most important in machine learning is to have the best data and to clean them well and to process them. Then in this case, yes, it seems that they told us that the University of the Basque Country is a big country, it's a big university, it's the only public university of the Basque Country. And then there are different researchers, and for that we contacted an expert on meteorology, and who said us that yes, according to his experience, the best would be from European agency. Then we contact the person in charge of this to change this kind of data in France, and see a convention. Thanks to that, we can use.
Okay. So my last questions. So you have shown that so there's no single optimization techniques that fit for all, right? So also in dealing with these variants, and to measure the quality of optimization technique itself, so we have to compare between the result and also the resource we use also for running this this optimization technique. So what about the, let's say, the benefit and cost ratio of the optimization techniques also you showed, so especially the best ones?
Not finished another optimization.
Yeah.
But yes, if I well understood, you're saying that yes, if optimize the computing consumption of computing power would be bigger. Yes. But yes, in our case, yes, we first of all the forecast models are based in small data. Then their consumption of and regarding the optimization, for the moment, our idea is to carry out the linear equation, and there also the solution of the problem would be easier. But what I would say, even it's true that later we want to work also in trying to optimize, but with machine learning based models. There, of course, the computational power will be much.
Okay, thank you very much, Professor. Thank you.
Any more questions? So before we conclude the event, I'd like to invite Dr. Raman for some closing remarks.
Okay, thank you very much, everyone, and special thanks to Haritza for the very great presentation. A lot of information here. I will just take like a little bit time. I don't want to delay the lunch. I'm also hungry, basically, right? So, and yeah, we will talk like casually later with Haritza and his wife here. Haritza has been here for 6 months, right? Almost 6 months, and it was great time for us, and I'm sure it was great time for the family as well, right? They visited much more places than I visited so far in my 7 years here. Okay, and yeah, and about this event itself, actually, this event is organized by IEEE student branch AUT, and the students are organizing this. I'm just basically, how to say, just sitting here looking, then something like that. And basically, what I'm trying to say is they have done great job, especially Afi here as the president or chair of the IEEE student branch, Ufini secretary, as the secretary, and Babar, I don't know, maybe he did not want any position yet, but he has been very active. We also encourage other students, if you have student or if you are a student, please contact them if you want to participate. We would like to organize more events, not just talking like this. We also would like to organize some event like sightseeing, go to Sky Tower, or have some mental health session, workshop, something like that. Just bring idea. We will get together how to make it real. And we have IEEE as the sponsor for this event, and also they would like to sponsor more activities from us. Okay, So yeah, if you think that you like this kind of thing, and or you think that this is not enough, you want more, then come, let us know. We welcome you. Thank you very much, everyone. And lunchtime. Okay. Thanks for the online attendees.